In Lesson 5.2, we're going to talk about best fit lines. One of the strengths of mathematics is being able to model things that happen in real life. So in our first example, we have a table that gives us some data about the time spent playing video games daily for selected ages. Now, if I just look at that table, I can't really tell what's going on. But if I use that table and plot ordered pairs that are related, then I can create a scatter plot and it will be more clear about what's happening. So let's do that. I'm going to treat each row of the table as an ordered pair, and I'm going to plot age on the horizontal or the x-axis and time on the vertical or the y-axis, and I'm going to put a point at 10,85. Notice that I have a grid and it's labeled horizontally with the ages and it's labeled vertically with the time spent. So if I go to where the age is 10 horizontally and then I go vertically to 85, I would put a point right there for that ordered pair. Now I'm having to approximate some of these values because they're not going to fall right on the grid, and that's okay. We just want to get the general idea, the general location of where that point would be. So now let's go to the next row and plot the next point, 1575. So I'm going to go 15 on the age, which is horizontally, and then I'm going to go 75 vertically and put a point right there. The next row is 2080. So the age is 20, and then vertically I'm going to 80. I'm going to put a point right there. One more together. If I go to 22 for the age, I want to go to 78 for the time spent. So that dot's going to be pretty close right there. Take a moment and pause the video and finish your scatter plot, then let's come back and compare. So your scatter plot and mine should look similar. And what I notice when I look at that scatter plot is that it's somewhat linear. So here's my line. I want it to be as close to the middle as possible, but I've just eyeballed this. If we have a negative slope, then that means as the age is increasing, which means I'm going in this direction, the time spent is decreasing, going in this direction. That's the negative slope, and that gives us a lot more information about what's happening in our survey than the original table gave us. This visual is much easier to understand at a glance. Not all data is going to be linear. If I look at the next scatter plot that's provided for me, it's giving me the age versus the time spent puzzling or putting puzzles together. So you can see that for younger ages, like 5, 10, 15, you've got about 12 or 11 or 10 puzzles put together in a year. But as the age increases to around 40, 45, 50, then the number of puzzles dips down to 8 or 7 or 6. And then as the age increases to older generations like 70, 75, 80, then you see that the number of puzzles put together is increasing again. So this is not something that we could draw a single line through. If I use my ruler and I try to draw a line, well, maybe I could draw a line this way, and that would show this negative slope right there, but then that ignores the data that's happening to the right side. Or maybe if I drew the line in this direction, then I have a positive slope, but it ignores what's happening for the younger ages. So what we would have to draw to represent this data would be something more of a curve like this. Okay, so that's not going to be a best fit line. We would say that this is nonlinear, and we could get into specific types, but for right now we just want to talk about, is it linear or is it nonlinear? And this one is definitely nonlinear. One word that's often used to categorize scatter plots is correlation. Correlation just refers to how closely the data fits the model. In our case, we're looking for how close does it fit a line, because we want the best fit line to be our model. But it doesn't have to be a line, it can be a different shape. We can talk about the correlation as being positive or negative, and that refers to the slope of the line. We can also talk about weak, moderate, or strong correlations. In this lesson, we're going to refer to that in general terms. We're just going to look at it and say, yeah, that's a weak correlation, or there's no correlation, or that's a strong correlation. But in our next lesson, we'll be able to pinpoint that a little more and tell it exactly how strong it is or how weak it is. Let's categorize these scatter plots that are given across the page here. And to do that, let's draw a line through the middle of the data. So if I look at this first graph on the left, then I could draw a line through the middle of it right there, and not many, some points are on the line, but it's kind of scattered there. So I would say that this is a weak correlation. You might say that it's moderate, and that's okay because it does kind of sort of look like it's a line. It's at least enough aligned that I can tell that it's a positive correlation, which means that we have an uphill line. We have a positive slope. If we look at the next graph, we can draw a line through that data, and the data fits closer to the line. So it's a closer correlation than the first graph that we had. So you might say that that's moderate. I would say this one is fairly strong. Like I said, we'll categorize moderate and strong a little more closely in our next lesson. This also has a positive correlation because it has a positive slope with that uphill line. For our next example, we could draw a line through the center of that data. It's somewhat linear. We could justify that that's linear, but I would say it's a weak correlation. The slope would be negative. It is going downhill. It's decreasing. So I would say that's a negative correlation. If we try to draw a line through our last scatter plot, it would be really arbitrary about how we drew that line. There's no real slope to it. So I would say that there's no correlation here. As you saw at the beginning of the lesson, it's very tedious to plot those points. So what we'd like to do is use technology to create the scatter plot for us. We're going to create a scatter plot in Desmos. So let's go to Desmos and get started. The first thing we want to do is go to the plus and choose table. And then in the table, we want to put our 2 columns of data. When I put my data in a table in Desmos like this, it automatically plots the points for me. Now I can turn that off by touching this green circle with the dots on it, and then it's not going to show up. But if I touch that again, then it's going to turn that back on, and that means that it's plotting those points. So why am I not seeing any points? The reason I'm not seeing points is because those ordered pairs are outside the window that I'm looking at. So I need to adjust my window. I can do that by go over to the wrench in the upper right corner where it says graph settings when you hover over it, and I can set a window. I have an x-axis window and I have a y-axis window that I need to set, and these are really easy to set. My smallest x value is 5, so I'm going to go a little bit smaller than that and put 0. And then on the other side of that inequality, I want to put something a little bigger than my biggest x value. And my biggest x value is 34, so I'm going to go up to 40. And then I'm going to do something similar for the y-axis. The smallest y value is 260, so I'm going to choose something that's a little bit smaller than that. I'm going to put 200 in for that smallest y value. Now I can always go back and change this if I don't like the way it looks. Maybe 200 is too small. You could go with 250 if you wanted to. And then on the other side of the y inequality, I want to go something that's bigger than the largest y value. Maybe I will go to 600. And then I'm going to change the step on that as well to count by 5s. This gives me a really good window for my scatter plot. I can see all of the points and I can see the correlation, and I don't have any extra white space around it. I can see just by looking at the scatter plot that this is a linear positive correlation. The slope is positive because the line is going uphill. In your notes, they tell you what the best fit line is, so let's go ahead and type that in and see how it looks with our data. So I type in y equals 12x plus 193. That's the best fit line. Those numbers have been rounded a little bit, but it's very close to the best fit line. And you can see that it goes right through the middle of our data. We can use this best fit line to make some predictions. So our next question says to predict the calories of a sandwich that has 18 grams of fat. Is go over to the next line in Desmos and just put 12 times 18 for the x, and then plus 193. So I'm substituting that x value, and then you can see it's giving me a y value of 409. For our next trick, we want to predict the fat grams of a 400 calorie sandwich. I'm going to type 400, and I'm substituting that for my y value in my equation, and then I'm going to type equals 12x, because that's what I'm looking for, plus 193. And when I do that, I get this vertical line which shows up in blue, and I want the intersection of those two. So that just makes it easier to find that specific value on the graph. We can take our best fit line, y equals 12x plus 193. We can replace the x and the y with words to remind us of what's going on. Y is calories, x is fat. So we could read that equation, calories is equal to 12 times the number of fat grams plus 193. And then since we know the number of fat grams is 18, we can substitute that in, and that gives us the number of calories, 409. 12 times 18 plus 193. We can find the fat grams of a 400 calorie sandwich by substituting 400 for the calories is equal to 12 times x plus 193. And to solve that without Desmos, we would want to subtract the 193 from both sides. On the top of the back side of the page, we want to predict the calories of the grilled cheeseburger that has 79 grams of fat. So remember, grams of fat was in the X column over here. And if you compare 79 to the values that we had, the highest value we had was 34 in our list. 79 is way outside of that. If we did go ahead and use our model, then of course we would substitute 79 for the x, since that's the grams of fat, and then do the arithmetic to find the number of calories, which is the y value, and we would find that the sandwich has 1,141 calories. Is that an accurate prediction? Probably not. It might be, but we just don't know. Other types of curves can be used to model data. Here we have a scatter plot that shows the price of stamps over time, and this does not look linear, but it does have this curved shape, which is called exponential. So they've given us an equation. The equation of best fit curve is y equals 1.1 raised to the x minus 50 power, and then plus 2. So since they gave us the equation, and that's for the blue graph that you see, we can use that equation to make predictions. As long as our predictions are within the data that we're given, then it should be an accurate prediction. But if it's outside of that data range that we're given, then we can't be so sure about the prediction. In this problem, x equals 20 means 20 years since 1900. So if my x value is 20, then I'm talking about 1920. And we want to use the equation to predict the price of a stamp in 1940. Our x value, 40. And then we just substitute in to the equation. Y, which is the price of a stamp, is equal to 1.1 raised to the 40 minus 50 power, and then plus 2. I can enter that into my calculator exactly like that. Here's what it looks like when you type this into Desmos. And you can see in our box here that we get 2.38, and a long decimal, let's just round that to the nearest tenth and call it 2.4. In our problem, the y value is in cents, so it costs 2.4 cents to buy a stamp in 1940. So the actual price of a stamp in 1972, or 72 years after 1900, was 13 cents, and we want to see how far off the model's prediction is. If we substitute 72 for the x and the equation that we were given, then we see that the prediction is 10.1 cents. If we subtract the 10.1 from the actual price of 13 cents, it's a difference of 2.9 cents. And that is our error between our model and the actual. Okay, notes are done, so it's time to get your practice done and then move on to your mastery check.